Now that we have set up Faraday's law, we are ready to calculate the energy in magnetic field. This is done through Faraday's law, and let us first understand what is the physics in it. You see, according to Faraday's law, when we change flux, this implies an induced EMF. Or equivalently, change in magnetic field implies an induced electric field. So, if you want to set up a magnetic field, right, you start from 0 magnetic field and go to some higher magnetic field, you will be inducing an electric field. And to set up magnetic field, you always need some current. So, you will have to work against this induced magnetic field to establish this current, and that energy goes into magnetic field. This change causes an induced electric field. To set up B, we need to set up a current, and this current is, when we set it up, working against the induced E, and the work done gets stored in B field. That is the whole setup. So, it is using these that we will be calculating the energy in the magnetic field. So, let us do that now. dW dt, rate of change of this energy in magnetic field, will be equal to E induced dot J r, where J r is the current density, over V, and I am going to put a minus sign. The minus sign is there, indicates that we are working against the induced electric field, right. Something similar to the definition of electrostatic potential, where we had the change in the potential equals minus E dot d L, because we were working against the electric field that existed and therefore pumped in energy. So, now we are ready to calculate this. So, what we are doing is, let us also make some pictures. Here is some volume given by this lined region, and I am setting up a J in this, right. So, I am setting up a current J r in this. And when I set it up, there will be an induced EMF working against the setting up of this current, and therefore, I will have to apply energy from outside, and the setting up of this current produces B. So, the energy given in to set up J gets stored in B field. That is what we are going to do, and we have already now written that dW dt, and just to make it magnetic, let me write WB is equal to minus E induced dot JR dV, where is the volume V in which we are setting it up. I want to convert this into magnetic field. So, I am going to write this as integral E induced dotted with curl of B that is being set up divided by mu 0 times dV. I am going to now use an identity, vector identity, where we know that divergence of E induced cross B is equal to B dot curl of E induced minus E induced dotted with curl of B. And using this, I can write this equation as I am after minus E induced curl B. So, this is going to be equal to integral of divergence of E induced cross B dV minus integral B dot curl of E induced dV, and there is a 1 over mu 0 all over. Now, the first term, this term is equal to 0 by divergence theorem, because I am going to assume B and E induced fall off very fast as you go far away. All right. So, that is the assumption, they are localized. So, I am left with only second term. Let us work on that term. So, I have gotten dW over dt equals minus integral B dot curl of E induced dV. There is a 1 over mu 0, which is minus 1 over mu 0 integral B dot curl of E induced, we know from Faraday's law, is minus dV dt dV. So, this gives me 1 over mu 0 integral 1 half d by dt of B square dV. Now, you may ask at this point, but the volume integral was only over J, or where J was not equal to 0. So, how can I now write dV all over space? Well, the answer is very simple. When I calculated this J, and there was an E induced going opposite I did integrate over this volume, but I could have written this volume all over the place. So, dV can always be taken over the entire space, and it will contribute only when J is not equal to 0. However, when I convert this into B field, the volume, wherever B is not 0, it contributes from there. So, I have now gotten that dW dt is equal to integral B square over 2 mu 0 dV. Since it is all over space, I can take dy dt outside. This implies that the work done is equal to integral B square over 2 mu 0 dV, or the energy density in B field is B square over 2 mu 0. So, we have gotten what the energy density is, like 1/2 epsilon E square in the electric field. Here mu 0 comes in the denominator. Let me also now tell you how this E induced dot J I can get in another way, very similar, but another way. So, let us apply an EMF to a circuit and set up a current. So, here is EMF applied, and as it is setting up a current, there is an induced EMF. So, there will be an induced EMF. So, correspondingly, there will be an electric field applied and electric field induced. So, if I were to calculate E total in this resistor or wherever the current is flowing, is going to be E applied plus E induced. So, if this is the resistor here, in this I am going to have an electric field which is E total. So, the Joule heating in the resistor is going to be E total there dot J R dV integral. This is Joule heating rate per unit time, and the energy supplied is going to be equal to E applied dot J R dV per unit time. The difference between Joule heating and E applied goes into the energy in the magnetic field that is being set up. So, the difference is equal to minus integral E induced dot J R dr. So, the total energy that is being supplied, part of it goes into Joule heating and the other part gets stored in the magnetic field. So, having derived now that the energy in the magnetic field is 1/2 B square, 1/2 mu B square over 2 mu 0 dV. Let us now look at some alternate expressions for W in terms of the current I and flux phi, and in terms of current density J and vector potential A. So, I am going to get two alternate expressions now. So, remember how we started. First, I will do for I and phi. Let us take a thin wire, and in this thin wire there is this current I. If I look at it little minutely, this is the thick portion of the wire. I need this thick portion because I am going to start with that E dot j, and here is this j going in this. Now, the rate of change of energy dW dt is equal to minus E induced dot j r dV, where the volume now is going to be over this wire, which I can write as dV as equal to, let me look at this thick portion again. Here is a section of it which I am going to call the area ds, and in the direction of current there is this dl, which is in the direction of the current. So, I can put that vector instead of on j, I can put it on the length. So, I can write this expression as minus integral E induced dot dl times j ds, which is the same thing. So, what I have considered is this thick portion of this wire, which is carrying current I, and in this thick portion I have this section ds, and I have current j, which is also the direction of dl, and I have written dW dt is equal to minus integral E induced dot dl times j ds. Since the wire is thin, it is very thin, cross sectional area is very small, we take E induced to be the same across its cross section, and j ds is nothing but the current I, and therefore, I can write dW dt is equal to minus I integral E induced dot dl, and this dl is over the entire loop. So, dl is going all around because we are integrating over the entire volume. This, now I am going to use Stokes' theorem and write this as minus I integral of curl of E induced dot ds, where ds now is the area enclosed by this loop. So, I can write with area enclosed by the loop. So, dW dt is equal to minus I integral curl of E induced dot ds, which I can write as minus I using Faraday's law. This becomes plus dB dt dot ds. Now, this partial with respect to dt I can take out. So, I can write this as I d by dt of integral b dot ds, which is nothing but I d phi b dt, where phi b is the flux passing through the loop. This is quite easy to understand. After all, this is EMF induced and this is the current. So, this is nothing but rate of power being pumped in. This is not surprising, but I wanted to go through this exercise so that you see how these manipulations are done. I could have written this expression right in the beginnings talking about EMF and the current. And therefore, I can now write dW is equal to I d phi b. Change in the work done or the amount of work done, if current is there, right, and I build up this current, I can write this as I times d phi b. And since phi b is linear in I can write the work done as 1/2 I phi b. That is the other expression for the energy in magnetic field. Next, I want to write energy in terms of J and the vector potential A. So, I have dW by dt equals minus E induced dot J dV. And from here, from whatever I did just now, for a volume where current J is being set up. So, let me make current J inside being set up, and there is some cross sectional area ds, and since this is an extended object, I can make those loops at each position, or better yet, I can think of this ds as infinitesimal right here and then make another section of this wire carrying J and make ds out here also. This is ds and there is this current J position dependent flowing in this also, and so on. So, that way I build up the entire volume. I have already seen that I can write this integral as integral del B del T dot ds, and along with this I have J dA. Now, just to make a little correction and make a better connection with what I have written, I should change this ds here to dA, and I should change this dA here to ds. Let me explain it once more. So, I have this volume in which current J is flowing, current density J is flowing, made it thick, and here is J in this. I am taking the cross section of this volume, let me make it through blue, as ds, and I am taking the corresponding area, showing it through blue, through green for this dl. Keep in mind that this region is very thin. This is dA. So, dA is this entire area surrounded by the wire. That is why I change it up there. So, what I have now is dW dt is equal to minus E induced dot j dV, which I can write, since j is only over this ds area, I can write this integral. I first do this dB dt dot dA, and then I do j ds, and that's the second integral. Now, B is curl of A. A is the vector potential, and therefore, I can write this as integral j ds integral d by dt of curl of A dot dA, where this A is the area. Now, I again use Stokes' theorem to write this whole thing as integral j ds d by dt of A dot dl, where now dl again is this along the loop. So, this is dw dt. Now, I will take this vector sign which is on top of dl to j and write ds dl as dv to get integral j dot dA, partial dA dt dV. So, what we obtained is that if I have this some region in which there is some j, I take a thin portion of it shown by blue and do my little math and vector calculus, then I get dw dt is equal to integral j dot dA dt dV, and therefore, dw is equal to integral j dot dA dV. Again, A is linearly dependent on j. So, I can write total energy as 1/2 integral j dot A dV. This is the third expression. So, we obtained three expressions for the energy in magnetic field. One is, let me write this in terms of energy density. So, one is B square over 2 mu 0. Second one, the total energy is I phi B. I can divide this by the volume. And third one is 1/2, or there is a half also, 1/2 j dot A. What I like you to do is show that 1/2 j dot A dV gives the same answer for the energy in different gauges for A. Now, just to compare with electrostatics, the three formula that we have derived, we had in electrostatics 1/2 epsilon 0 E square as the energy density. In magnetostatics, we have 1/2 B square over mu 0. In electrostatics, I had half Q V as the total energy. Here, I have 1/2 I phi B as the total energy. Then I also had total energy in electrostatics as 1/2 integral rho r V r dV. In magnetostatics, I have 1/2 integral J dot A dV. So, you see there is this kind of correspondence between the two. Let us now solve an example using whatever we have done. This is problem 33, chapter 7, Griffiths. And this problem is as follows. An infinite cylinder of radius r carries surface charge density sigma. It is set spinning with final angular speed omega final. Then we want to know how much work will it require, and we want to do it in two ways. The two ways are, one, the way we derived the energy in the magnetic field, another will be using the expression for the energy directly. So, one would be by calculating the induced electric field in quasi-static approximation and finding the work done against it when setting the cylinder is spinning. And the second way is by finding the total energy. So, let us see what is being done. I have this cylinder that carries surface charge density sigma, radius is r, and we start slowly or fast, does not matter, as you will see in a minute. We start spinning it. Let us see what happens when we spin it. So, when we are giving it a spin like this, what is going to happen? This is going to be equivalent to a surface current K being set up. And if there is a surface current, is going to set up a magnetic field inside. So, as we increase omega from 0 to omega final, the corresponding B changes, and this gives rise to an induced E. So, here is the cylinder with sigma, radius r, and it is being given a spin omega, and therefore, in the cylinder there is this K being set up, and this gives a changing magnetic field. So, dB dt is greater than 0, it is increasing in the positive. Let us say this is the positive z direction, is increasing. So, what would happen? Let us see. I can draw an analogy with the equation or the Biot-Savart law equation, as we did in the previous couple of lectures earlier. If I have, so let me draw the analogy with Biot-Savart law, and here I would like you to recall our lecture on how to calculate E induced from dB dt using Biot-Savart law like equation, and this is applicable in the quasi-static approximation. So, suppose I had a cylinder where I had a current I going. In this case, this will produce a B field like this. What is happening in our case? In our case, the current case, I have a dB dt, which will induce an electric field. Now, remember here the equation for the magnetic field is curl of B is equal to mu 0 j, or integral B dot dl is equal to mu naught I enclosed. In the case of Faraday's law, I have curl of E induced is equal to minus dB dt, or I am going to have integral E induced dot dl is equal to minus d phi b dt. So, by this minus sign, what we are going to have is that the induced electric field is going to be the other way. E induced, and it is very easy to calculate. I am going to have from this equation, the equation given here, I am going to have E induced at the radius times 2 pi r is equal to d by dt of B times pi r square. or E induced at the periphery is going to be equal to r by 2 dB dt. So, we found what E induced is. So, physics wise, I have this cylinder. When I set this in motion, I get a K, which gives rise to a B field, and this in turn is giving an induced field E induced in the opposite direction, and therefore, is going to apply a torque which will also tend to rotate it this way, and I have to apply a force to set it up in motion against this torque, and that is the work I will be doing. I have already calculated E induced in terms of B. So, I have written E induced at R is equal to R by 2 dB dt. B magnitude is inside mu 0 K. What about K itself? K is going to be, K is the current per unit length. Per unit length, the charge I am going to have is 2 pi r sigma, and is going around with the frequency omega over 2 pi, which is going to be equal to r sigma omega in the phi direction. And therefore, B is mu 0 r sigma omega magnitude. B dot or dB dt therefore, is mu 0 r sigma, which are constants, d omega dt. And this means E induced at r is r by 2 mu 0 r sigma d omega dt, which is equal to mu 0 r square sigma over 2 d omega dt. This E induced is going to apply a force on each charge. So, let us see, if I make the cylinder like this and take a strip on the cylinder here, of angular spread d phi, and this length is unit length, let us say 1 meter. The force due to E induced on this strip is going to be in the minus phi direction, and the force is going to be the charge on the strip, which is going to be d phi times sigma, and this multiplied by mu naught r square sigma over 2 d omega dt is equal to the force. So, once I have calculated the force, this is going to create a torque. So, torque is going to be r times this, so which is going to be r times this force, and therefore, on this small strip I have the force which is equal to, So, mu naught sigma r over 2 d omega dt times sigma r d phi, and torque is mu naught, therefore, sigma square r cubed over 2 d omega dt times d phi, and torque sense in all the strips is the same, and therefore, the net torque is going to be equal to mu naught sigma square r cubed by 2 d omega dt times integral d phi 0 to 2 pi, which gives me pi mu 0 sigma square r cubed d omega dt. So, to move, to rotate the cylinder by d phi, the work done will be d w equals pi mu 0 sigma square r cubed d omega dt times d phi, which is equal to mu naught pi mu naught sigma square r square d omega dt times omega dt, which gives me pi mu 0 sigma square r cubed omega d omega, and therefore, the total work done is going to be equal to pi mu 0 sigma square r cubed 0 to omega f omega d omega. You see, independent of the rate at which omega is increased. So, this is going to be equal to pi by 2 mu 0 sigma square r cubed omega f square. That is the answer. Now, let us do the same thing through energy method. Calculating the energy change. If I were to do that, we will find that when this fellow is rotating with omega final, the energy density is going to be B square over 2 mu 0, which is equal to mu 0 square k square over 2 mu 0, and this we have already calculated is equal to mu 0, k is sigma omega r, so the omega final square over 2. So, this is 1/2 mu 0 sigma square omega final square r square. So, energy per unit length is equal to pi r square times 1/2 mu 0 sigma square r square omega final square, which is pi by 2 mu 0 sigma square omega final square r raised to 4. So, I am getting the same answer except for this r raised to 4. In the previous calculation, I had an r cubed. So, that mistake I will leave for you to check. Rest of the quantities are the same. So, let me just write it here, except for the difference in power of r, everything else is the same. This is not surprising, because after all we derived this expression b square over 2 mu 0 from the expression for work being done against induced EMF. So, that is precisely what we have calculated in the previous calculation. So, the answer should come out to be the same. So, let me leave you this, check how the power of R came out to be different earlier. Obviously, there is some missing step that I will leave for you to do. So, conclude we have calculated the energy in magnetic field by finding out the work done to set up the required current to get this field, and then we solve one example. Thank you.